everyone for it. And so today we will talk about this R-triviality. It's some weaker version of rationality, and we will just see for the underlying variety whether that will be for this proper projective similitude. So for first, let's see what is this, that proper projective similitude. So for the whole context, K will be our best field, and we will go with characteristic different from 2. And we will basically for our quadratic forms. We use the underlying vector space, and so first see what is the need. So these are all endomorphisms of V. For some constant, non-zero constant, and so for here we can actually we call these elements. This is form of group, and it's a group of similitudes. Here we can have a group homomorphism. We just take this F to this constant A. And what is the proper similitude? So it's like those similitudes are determinant where basically this 2n is the dimension of. So basically these are groups I said, but you can have to see this as a rational points of algebraic groups. So in that case, a k rational points, and so this is we get the proper similitude. So in our chapter we have looked for the projective similitude. So that is nothing but we will quotient with the scales. So this is the so we will talk, and this is actually an example of a algebraic group which is connected. Adjoint, for example. And basically in 2 weeks back, Rini talked about the with 2 groups of G and H, and this actually Margaret have a translation where for this particular algebraic group, he gave a translation to whether this underlying variety, this is R-trivial or not, with the help of two other groups of the multiplicative group of fields. So first we will, and basically we have to rationality is the strongest version. That implies doubly rational. And another weaker version, that is the R-trivial. I'm not going to the exact definition. So, which is this one is just so birationally isomorphic to this sum. And here, if you have that variety, it's like have a factor that is isomorphic, then we say. So basically, but that Markov translation. So from there, you can see from this relation that will help you to show for the when the underlying varieties are trivial. Also, if you can get some examples where that it is not R-trivial, in that case, you can immediately then say, okay, the underlying variety is also not rational. So that's the most applicable part. So first, let's see what to get the Markov translation. What are the two groups? So for that, we have to get back to the image of that group homomorphism. So this mu. So that is so which is that A, and actually this is half the we know is as a similarity factors. So another version it is like that, you can which are isometric too, and this is from a so if you have, we call this as a group of similarity factors. Of this quadratic forms. And you can notice that K star is contained here. Also, this G will be as a remark. The K star, if the dimension of the form is odd. So dimension of the form is the dimension of the underlying vector space. So, and for the whole context, usually I will, if I don't mention means I will go for the dimension of the quadratic form as an even dimension. Now, I just want to get another notion that is hyperbolic. So, this is the hyperbolic plane. And any form that is, like we say, hyperbolic, if that is isometric to some in copies of this hyperbolic plane. And note that G of phi, that will be the whole K star if the form is hyperbolic. So actually from here we will get the another group which will help you for the translation. So for that, before that I just want to see how under the norm map of a field extension this group acts. So for that is Charlotte norm principle. what it says that if you have any field extension, not and this is the norm map, then basically you have
You want a finite field extension?
separable.
Yeah, finite.
Yeah. So, and this is nothing but the scalar extension of the form. So it will sit inside this under the any extension. It will sit inside this G of Q. So from here, we get, okay, when the form is hyperbolic, it will be the whole set, and when we will take the norm, it will go to the, so for the next we have is that so what is that? That's generated by all those norms such that this element is a finite field extension. And this form over this extension field is hyperbolic. So note that when the form this phi of L is hyperbolic, then G of phi L will be L star, and L star, if you use that shallow norm principle, then it will be sit inside that G of Q. So from there we can have, so it will be a subgroup of G of Q. And when here basically we denote that we are just taking the, because case study is contained in G of Q, so we we are just denoting this one as H of. So this two group, it from here we will the statement for Marguerite to determine the projective similitude. So what is that result? That so this PSim plus of phi is R-trivial if and only if G of phi of for all field extension so he gives this translation where you have to with these two groups it will help to get the underlying variety of this variety, whether that is trivial, and if for some, and here we have mentioned it is for all extensions. So if we get some extension example or some extension, these two are not equal, in that case it is not trivial. And for the relation that the implication, so we can say that is not rational. So first just I will like to say some cases where some low dimensional where this result, material result have the positive things, I mean that these two are equal. So
Looking still on the ground.
oh. let's see. So first is that if you have the dimension for the quadratic form is 2, it will be R-trivial. If you have the dimension is 4, it will be R-trivial. Now if you have, and by the way, so for the odd dimensional, I mentioned that it will be the whole K star, and also, so when it is odd dimensional, this h of q, that will be also the K star. So in K star square, sorry. Yeah. So here is the definition of this h of q. So that is also there. So if you have odd this is the Pfister form. So how this form looks is like tensor product of this type of binary forms, which I give this notation also because later I will use this, and these are basically like x square minus ci y square. If you can think this as a like this.
This is confusing. Do you want to put a tensor product after the equality, or do you want to put the?
So this is just the notation, and it's like because for abbreviation later I will use this, and basically for each terms I just this looks like this. So for this Pfister forms also we have this for all extension. Further, if you have some Pfister form that is tensor with some form where the dimension of this is odd, then also it is R-trivial. Even if you take n as any integer and n copies of 1, that will be also R-trivial. Moreover, in this last two cases, we actually have the R-stabilization. So the first case where this we can get an example that Remy actually also basically his construction is based on that that's the multivariate construction when the dimension dimension is 6 and the discriminant of the form is non-trivial. And also additional some invariant of this Clifford invariant that is a division algebra. So Remy has shown some construction, some examples. So this is the first example where first example means in the first dimension came where this R-triviality fails. So okay, so today I will exhibit some examples where because in the point that it is shown that it have to be holds for all extension. So first we will see some result where we will show this R-triviality holds, and in some example where we will exhibit in some field it is holding, but in some extension it is failed to be R-trivial. So sorry, not R-trivial. R-trivial, not these two are not equal. So first come with that the statement that if the height, I am coming to the definition of height. So if the height is at most 2 of the quadratic form, then this is R-trivial. So what is the height means? So first, so this is our word with this is our joint word, and then I will come to first see what is the height. So for any quadratic form, we can write it as its anisotropic part, and so this is the width index. And this is the anisotropic part. So anisotropic part means it will have the, if you have it have only no non-trivial solution. So and for over the extension, this is equal for this extensions, we will have several width indexes. So in some extension, so if that is isotropic, so we will have some another part of an isotropic part, and then the width index. So in the extensions, so these collections, we call this is the splitting tower, and height is the cardinality of this minus 1. So for example, for the Pfister forms, we know that if the Pfister form is isotropic, then that will be hyperbolic. So in that case, the Pfister forms have the height is 1. And as I remarked, if height is 0, that means the form is actually hyperbolic, and so this width index will be half of the dimension. And as I mentioned that it's a scale Pfister. And so before going to the proof of our theorem, so there are actually some results where they shown the R-triviality with so many other conditions, with like only restricting which are also falls under the condition of height of 2, but they are limited in the sense. So it's Karimala tenure wise in 2012. So if the discriminant is trivial, then trivial. So one is that if you have the dimension of the form is 8 and so all of these conditions, they are all falling under of this height at most 2. In this result, what are they are actually all in the under height 2, but they are limited. We don't know from here what about 14 dimension, 16 dimension. In our result, if that is just height at most 2, then we can say that is R-trivial. So now I will go back to the, I would like to prove the theorem. So before that, some instrumental lemma I will just like to state. So you are just taking an anisotropic form. Then there is this quadratic extension. Such that this A will be a norm from the extension and the V index over L will be greater. So shortly I am giving the proof of this. So we have this form for this, so that implies and for this we will have there exists some binary form, subform of this phi. Isotropic, and as we have our form is anisotropic, so the discriminant of this that will be that is not a square. In that case, we can take that quadratic extension. This and
As we stated, we could take beta equal to phi. There's something missing.
sorry, right?
Beta.
Yes, beta is a subform of binary subform of the phi.
But you didn't, okay, binary you didn't say.
Yeah, okay. So it's and we will now this one is hyperbolic, so A will be from a norm from this extension, and over the L now this form phi that will be isotropic, so we will have that V index will be greater than this. Fine. Now we come back to our proof when height is at most 2, that is R-trivial. So when we define, we already So this is the proof of the theorem. So one thing we already know that this is a subgroup of, by definition. So we are interested to prove the other inclusion. Okay, so for the other inclusion, just consider element from this. Now I will use this lemma. So by this lemma, we will have a quadratic extension, and exactly that extension is with the discriminant of the binary form, and now so in our current scenario, here is our K, here is our L, and for this phi we have the decomposition D, phi 2 such that over this L, the anisotropic part of phi will be phi 2. So now we have this A is from G of phi, and we, as we seen in the lemma, that A is also from G of, so we can have that A is actually, so it is from this two and it's a sum, so it will be in phi of 2. Now here again we will use the lemma. So for that we will get another quadratic extension. So for this, I give it a and the norm is from the, so here one thing I will mention that that's called biquadratic lemma. So what that tells that if you have two quadratic extensions, and if you have, so it's like if I say it as a K1 and K2, so the norm from K1 that will be actually in the norm of, if I say as K3,
K1 is K square root of beta.
K square root of beta. Yeah. So here we are exactly in the situation. We will use the biquadratic lemma because we already have that here. This is from this norm, and also earlier we know that that is from a norm from this. So we will have the A is a norm. Here. Else is the square.
You need to find this this object that you are. You already use it beforehand. You use it everywhere. So
Okay, so it's like for this norm map of the whole multiplicative field, we are just using as a short this notation. Okay, so now.
One in the box also for this.
And so for by definition of the H, so what we need that element should be from the norm, and at that extension that need to be hyperbolic. So already we have that. So over L dash, this form is so already we have this. And note that over because of over L, these two are same. So that's another extension over. As we have that anisotropic part of over L of phi is same as phi 2 of L. So we can write this to our equal. And we have this is greater. And we are given that our height can be at most 2. So already we have these 3 collections of the width indexes. So that means that, so height at most 2 means the index we can have 3. So here this is the most. So in that case, at over M it should be hyperbolic. So here we are using phi of M hyperbolic. So this is hyperbolic and A is a norm from the map. So with these two we can say A is in the H of Q. Now we only get for that sum over the best field case.
The I of phi 2 over M is still bigger than the I of phi 2 over L prime. I don't think that we know this. It's greater than or equal to, no?
Oh, okay.
It's the I of phi 2, which is already.
Phi 2, we have for phi, this one is strictly greater than we have, and it's better that I should just only get this. I think that would be better.
This is, yeah, I don't think that the phi 2 was smaller than phi. No, it was a subform. So I don't think that they have the same I.
No, because over L.
But you say equal, and I don't think that they are equal. That
So over L, this anisotropic part is the same with the phi 2. And so over M already we have over M this phi 2 is isotropic. So we will have this phi of I of phi, that would be strictly less than phi of L.
Strictly bigger, yes.
Yes.
But I just remove the thing above this here, isn't there? And no, without inequality, it's strictly.
Yes.
Yes. How much is that?
It's okay.
Yes.
So now we are with the thing that that G is equal with H, but it's only over the base field. And the Markov criteria is we have to get it for all extensions. So how that one is satisfying here? So for that, if you have any extension over K, for that height of the form will be so you will have this. This basically says that now we give some result where it is whole. Now let's go for some example where we can see, okay, this R-triviality fails. Though in some sub-extension this G and H are equal. So for that, first I will define some lambda function. So what is that? It's like you are just taking some non-zero elements from the field and you have the multi-quadratic extension. This lambda is how it defines. So one thing note that if R is 1, then this function will be trivial. Then these two will be equal. So it will be definitely equal. R equals to 2. But can you say we just define that biquadratic lemma? That is exactly the thing when R is 2. So in that case also, this form is lambda is trivial. The first thing for R equals to 3, it comes up that this lambda is not trivial. Sorry?
Square, because line of R1.
So this non-triviality will help us to construct the example, and also additionally I will state some result of Sivatsky. What it says, so if you have a triquadratic extension will have a linearly disjoint extension K dash such that this lambda of K dash of square root of A1, A2, A3, that will be non-trivial. Now we are really ready to get some examples where this is not R-trivial. One thing note that the Markov statement that have the which is the example dimension 6 non-trivial discriminant is giving the not R-triviality, and for dimension when the discriminant is trivial for 6 dimension, it is actually rational. So for the first lowest dimension, we can expect for not R-triviality with trivial discriminant, that is 8. And exactly in our example, we will show that the dimension is 8 and discriminant is trivial. So for that, I will first we are taking our field as C of K, and okay, fine, I should mention this. I have the so we are taking that K as C of X, and this AI as X plus I for I1, 2, 3. It is assuring me that this is a tri-quadratic extension. Now I will get by Sivatsky, I will get that another disjoint field K dash such that so this is my K dash, here is my and we are taking iterative power series. Just note this one as capital K, this one as K dash. So this is just so by Sivatsky's result, we will here our lambda will be not trivial, and so what is the form? I have just give all the setup of the field. So the form is a form over this capital K. And note that you can see this basically this form can be actually rewrite as a sum of two forms. So from here actually someone having the dimension is 8 and discriminant is trivial. Also and over the field K prime dash here, so it will be isomorphic to this lambda. Which is not trivial. So over this K prime dash here we will have G not equals H. But also note that one thing, any finite extension over C of X, the norm map, that will be it is surjective. And in that case, how this lambda is defined, that lambda will be trivial. So this extension necessarily it will be, because over here we are having this is not trivial. So this extension is transcendental extension. And also, so what about in the over this K, you can note that this already the form is, because it's a sum of two-fold Pfister forms. So this is a form in I2. And the homological dimension of the field is 3. So basically I4 of K is 0. And this is I can take it as a lemma. I'm just using it. So if we have some form from I2 and I4 is 0, then G and H are equal. So over this field, it will be equal. So in this underlying field, you are having these two are equal, but in some extension they are not equal. So in general, then it's not actually R-trivial. And here, the Clifford algebra of this extensions, these forms. So basically, it will be come up with, or I can just write here also it will be the two biquaternion algebra. So the index of, okay, sorry, I just missed one. Index of the Clifford algebra need to be at least 4, and here it is exactly 4. So now here we have that the index is 4. Now what about it's in I3? So for that means that when the Clifford invariant is trivial. So another just example. I will state. So we will have, here we are just taking that C of t as a small k, and then capital K this field as also we are considering here it is for this fact we will have that this is a for this fact, so actually we will have some non-zero AIs. So we can have this is a 8-dimensional extension. Now we just need this one because the Sivasky's result only want to have some triquadratic extension. So again by Sivasky we will have another k dash over k, and we are constructing another so how will be the form? So here we are taking the form these are actually 1, 2, 3 except the implicit. So dimension of this form will be times 2, so 14, and cohomological dimension of the field is star is 4, even variant is 16, and also this form you can actually rewrite it as so it's a sum of 2 3-fold Pfister forms, and means basically in that case this phi is actually a form from I3 where it basically means the discriminant is trivial, it is the Clifford invariant is trivial, and dimension is even. So what is the fact that for the earlier example we have the index of the Clifford algebra it is 4, and where we are actually able to get one example over this 5 we will have that this is where this is not R-trivial. Here also it will be in the same way.
Use some kind of multi-index notation which you didn't define. With the PI and AI. I mean, you did not define these elements.
So I am taking those from. Oh, yes.
No. Look here. At the when you define phi, on the right hand side you have a T index capital I and an A index capital I, and you did not say.
These I's are from this
I know what, I see what I is, but what PI and what AI is, you should maybe say.
Okay, so this one I have just choose. No?
You mean Ti? I is a subset, yeah?
Yes.
You mean the product of the corresponding elements?
Yeah, it will be like
let me just write down what you mean by Ti and by AI.
Yeah, it's like I'm just taking all these combinations.
Do you want to?
Yes. Three. From here also it can be changed. So if we have to write,
I think you understand the picture. Maybe dot dot dot. I mean,
yes.
it just suggested to define the notation, but now we don't need it anymore.
Yeah, this is like enough of this. So here also with that, because of this reverse, you will have this K prime that will be not trivial, and in the same way that it will be the form this G. That will be isomorphic to the K prime. So it will be again that it is not a trivial where it is in of all this. The lowest dimension is 14, and we can get with this homological dimension 4 with trivial discriminant, trivial Clifford invariant, and this dimension is 0. So this is the whole story for today, that where I just want to exhibit one positive result where we can see R-triviality, and mainly basically the second last example is the first example to see that okay, that can be happen that in some extension it is equal, but in some extension it is not really fails to be equal. So